Welcome and very good evening. Welcome to our podcast. And we are thrilled to introduce today our distinguished guest, Dr. Sergio Sevillano Munoz, who is doing her postdoctoral at the celebrated Durham University, United Kingdom. Dr. Sevillano brings with him an impressive academic background, having earned his PhD in particle cosmology, pursued applied mathematics and theoretical physics at the University of Cambridge. His research focuses primarily on scalar field dynamics and their profound impact on the late time universe. Dr. Sevillano has shared his expertise on crucial topics such as Hubble tension with scalar fields and how to study modified gravity at prestigious institutions like Perimeter Institute, Newcastle University, University of Southampton, and University of California. We are honored to have him with us today to share his insights and explore on different frontiers of cosmology. Let us please join and give a warm welcome to Dr. Sergio Sevillano Munoz. Dr. Munoz, a very warm welcome. We already have got questions coming from Pavan Gaonkar and Vishnu Prasad. Definitely, our main objective is to help the subscribers and answer their questions. But before that, we will set the stage and the ball rolling. My first question is that we tell that the role of scalar fields, I mean to say, in evolution of the late universe. What do we mean by scalar field and why do we call them scalar field?
So scalar fields is a notion that it's has been important for really long time, even earlier than the role that they take now in particle physics or cosmology. A scalar field it's a notion for, well, you have like the word field that is very known in classical mechanics, that basically is something that takes a value at every point in space-time or in space. In classical mechanics, now space-time when you're talking about kind of general relativity and cosmology. Now, the important thing about scalar fields is that it's not something that is very far away from our normal experience. For example, we know that all around us, everything is filled with these scalar fields or vector fields or tensor fields. The best example for a scalar field that I like to put is normally like the temperature in a room. So for example, the temperature in a room is a continuous function that takes different values in the different points of space. And of course, the change of this function is going to be smooth. So when you have some temperature at some point, you know that the temperature at the next point at least is going to be like a continuous function if it's going to change. So because it takes a scalar value, so basically it takes a value, it doesn't have a direction, so it's not like a vector at its point, that is what we call like a scalar field. Now, if it had a direction at each point and also a magnitude, so a value, that will be something that we call a vector field. And the best example for that, for example, is the wind in a room. So you know that the wind is not enough to know what is the magnitude or the intensity of the wind. You also need to know what is the direction that is pointing at each point. Now, once you have like this notion for scalar fields, they are very important because that's it. They basically take some value at each point of space-time, and depending on the value that they have and how they change in time, they are going to have one effect on the universe or another. It was proven that the best example, well, or the most important scalar field that maybe we all have heard about is the Higgs boson. The Higgs boson is very, very important in particle physics because depending on the value of the Higgs boson, so where the Higgs boson is, you know, like it has some potential that it looks like a W, a double well potential it's called. And normally in the early universe, it is said that the Higgs boson took the value, like it's normally set at 0, like in the origin of the axis. When the Higgs value is set at 0, all particles in the standard model, well, all quarks, like the fundamental particles, would be massless. So they would move at the speed of light and you would not be able to generate the structure as we know it. But because the potential has this W shape that I was talking about before, once the Higgs moved from the top point to the one of the minima, so it's a W, so one of the minima of this W, suddenly the value of the Higgs was non-zero at that point because it moved from the center to some place. So it became from 0 to some other value. And that new value of the Higgs is what gives mass to all elementary particles. So we know that there are scalar fields around. They are very important in cosmology because they are normally they can be very easily homogeneous. They don't point into any direction, and right now they are very important for cosmology, not because they are thought to be around, but because the easiest type of modification to the to any kind of cosmological tension that we see around, the best type of kind of solutions for those tensions normally come by adding scalar fields into the universe, because they will make the universe to expand in a different way, for example, or the structure to form also in a different way. It's the simplest thing to the model of gravity and the model of, well, cosmology and standard model that we have right now. The next step you can take is adding scalar fields. So that's why they are so important, because they let us know how the theory may look effectively at low energies.
Thank you very much. Actually, that actually clears a lot of doubt, because we talk of scalar fields and the evolution of universe, etc. We'll go on and take the first question, and I will be learning a lot from you. First of all, that's a wonderful explanation, very easy to understand. Now, Pavan Gaonkar from India is asking, sir, do you think we will be able to discover the theory of everything in our lifetime? And also, why do you think the theories or new ideas are not getting noticed apart from string theory?
So, well, that's a lot to take, and I don't know if I have like the expertise to answer that. In my opinion, I mean, I wish we get the theory of everything, or at least the closest thing to that in our lifetime, so I get to see it. And that's, I mean, my base answer. But I really don't know. It seems that we are right now in a very kind of stuck, but in kind of like in fundamental research. But it's also true that when you read kind of papers from the 60s and 70s and so, people used to think that in the past they used to go very quick, and now and at that point they were stuck in the evolution of kind of fundamental research. So I think that we are not in a different position today. We are trying to make these new discoveries, and it's true that in terms of theories of everything, the best contender right now is string theory. The reason why I believe, and there is like a lot of debate lately, like in Twitter and in the social networks, is they had like a really well kind of like public relations in the 90s mainly. So it's true that they kind of at some point maybe they oversold it. I'm not saying that it's not good. String theory is the best attempt we have to understand the universe, and I think that I don't study string theory personally, but I know many people who do, and many people who went to this theory of everything track, understand all the mathematics behind physics, and trying to get to get an answer out of it. And the only thing that I can say from my standpoint of being like a phenomenologist and a cosmologist is that all of these people that I consider really smart, that they have tried to find a theory of everything, they always end up rooting for string theory. There is something on it that is like the best attempt that we have been able to do to unify quantum field theory and general relativity that cannot be ignored. And even in the worst case scenario of finding of that string theory is not the theory of everything, right now it's just a formalism that the people are still developing. Even if string theory is not the final answer, it's going to be like knowing very well how string theory works and the formalism it has to explain the fundamental nature of our universe is going to be very helpful for whatever is the theory of everything that is going to be around. So I don't know if they are getting a lot of attention or not, but it seems to be very powerful in order to describe all the things that we are not able to answer yet.
Thank you. That was awesome. One question is that when you and Dr. Jessica also came in, there is in Durham University that is called IPP, Institute of Particle Phenomenology. In general, what we mean by phenomena is something which is happening. So, what does it actually mean?
Well, I don't know what is the root of phenomenology. The way we talk about phenomenology normally in physics is it's quite curious. Normally, you have kind of experimentalists, fundamental researchers or mathematical physicists in the two ends. So experimentalists or kind of like astronomers, for example, for astronomy, they are the ones that gather data and do all the numerical statistical studies of this data, so that we can get a final value, a final phenomena, in a way, like a phenomena in our universe. So, for example, you have all these astronomers and also part of cosmologists that they have these awesome telescopes, and they do all the data analysis of the observations they get, and they find that the universe is expanding at some rate, for example, at some speed. So that is one side of physics, probably is the closest one to the roots of physics, of just going around and understanding what is going on in the world. And then you can go to the other end. So let's go to the two extremes. In the other end, you have these almost mathematicians that they are trying to find a new theory of everything, or the new way of explaining what is the fundamental nature of our universe or some subset of the universe. So you have these two very, very separated. It's true that when you go maybe 100 years ago, they were both very close together, because physics was not as complicated as today. I'm not saying that it was easier. I'm just saying that it wasn't as complicated. So you could do both of them at the same time for most of the times. But right now, physics has been very, very specialized. We have lots of people working on it, so it's very special. So you need people in the middle to basically translate what is going on in in the fundamental research to what is going on in the experimental research. That is normally what is called the phenomenologists. So they take the theoretical kind of equations and models that have been produced from the pure fundamental research, and try to and we try to take those equations and predict what kind of impact those new equations or those extensions of the fundamental theory of everything or cosmology would have on our universe. And we get kind of like a value out of that. So we expect that a string theory, if they are around, there is going to be, for example, a scalar field that we predict should be around. And if there is a scalar field, if it moves in some way, then it's going to have some impact on the expansion of the universe. So we make that, basically we make that is what phenomenology is. We make that prediction on the impact that it will have on our universe, or in particle theory, like in colliders or in different sites of the universe. And then after that, once we have the prediction, we can compare with the data. So we are translators, in a way, from the fundamental research to the experimentalists, so that we can compare both of them.
Right. That means this actually brings automatically to our next point of discussion, is that so theoretical cosmologists or people are those who are actually, as you call, translating the observational data which is being carried out by JWST or very big high telescopes, how they will actually fit in. And then we get a kind of a complete theory of whether whatever the predictions are. So in that case, Dr. Sergio, whatever the mathematics that you're doing theoretically, sitting at your office, etc., is there any scope that you go to the telescopes and you see them and then try to find out the disparity and again go back to the calculations, or is it purely sitting on a pen and paper and doing all the calculations?
Yes, there is some back and forth, mainly because on a more kind of subjective reason, like in the sense that you want your work to be related to the to the trends in physics. So for example, if you have it is very interesting, and this is I really like doing it, like just from the theoretical standpoint, trying to predict what will happen in the universe, just for interest, to know what, like, how could we describe it. That is interesting itself. But then you actually, we are many physicists, like in the frontier of research, trying to find the theory of everything. What in the end we need some coordination, and that coordination makes leads to the fact that what you're saying, that normally you have like the experimentalists or the new telescopes and people working on the data analysis of all the observations that they do, they get some new prediction not prediction, but some new measurement. So that new measurement is going to normally motivate the exploration of certain things in the cosmology side. So it kind of goes back and forward. Normally, you motivate an experiment by having some predictions, because the experiment wants to check if those predictions are true or not. And also, new measurements will motivate the seek for new different predictions and new explanations for those measurements that was done. So in a way, they go back and forward. Yeah, but it is not normally the case. Yeah, I wouldn't be the one that does the data analysis most of the cases. In my sense, there is these long papers, as you were saying, JWST collaborations, JWST, sorry, or DESI recently came out, and they are these big papers with all the data and all the analysis and that they provide. The one that I take, I give for granted that is true, although I don't. Well, it depends. Like there is some probability for some errors to be around, but they always quantize that probability of errors. And once I have that data, I just take it from those publications and try to put them against the models that I'm describing. So I don't know if that was clear.
Right, yeah, absolutely, absolutely. We got one question from someone called Priyo. Sir, what is minimal and non-minimal matter curvature coupling?
So that's a very good question. It's kind of, yeah, I would say. So okay, so for this we need to kind of go into the way we, yeah, I'm going to, I knew that you wanted to talk about this. We have to go into modified gravity realm. And I saw that, for example, there are many different theories of modified gravity. So well, let's start for what we kind of know. We know that that the way we describe gravity is through general relativity. And general relativity is a theory that is very, very complex. And fundamentally, it seems to be very close to what it's right in the way that there is a space-time. This space-time can take, well, you describe it using for differential geometry. And this space-time can be curved and can take different shapes and geometry, basically. So depending on the shape of the space-time, the matter sitting in this space-time is going to react in some way or another, or is going to evolve on some way or another. Normally, the way it works in general relativity is that you have the matter coupled what is called minimally to gravity. What that means is that the gravitational sector, so whatever says how strong is gravity how gravity relates to the curvature and the curvature relates to gravity, it kind of goes both way around, that is made through what is called the Einstein-Hilbert action. You don't need to understand what that is, but basically is what Einstein came up with because it's the simplest thing you can do in order to describe gravity. So that's the kind of like the setup. You have general relativity, but general relativity is not a force. It's not just an interaction between matter. General relativity is a formalism to understand gravity. And once you have that formalism, that base, you can start saying, okay, we have this base. Now I'm going to say how gravity is going to work, or how matter, when you have two masses, are going to attract each other. The way Einstein's gravity, so the one that he came up with 100 years ago, does it is by saying that you have matter coupled minimally, it doesn't matter what is this name, but minimally to gravity, so that when when you have matter around a space-time, it's going to start curving the space-time around it. But also, once you have another set of matter in other side in a space-time that is curved, suddenly it's going to evolve in a different way and it's going to start falling into the curvature. So that's how it explains basically that two things come together naturally. So this is the standard way that works in general relativity. However, for this, we had to make some kind of assumption that it seems to be very right, I must say, but we had to make an assumption in there. And that assumption is that gravity goes by itself, like it's just how it's described by Einstein's gravity, and matter is only coupled minimally to gravity. So in a way, that means that they are kind of like these two sectors, pure gravity and matter, are kind of split. And that is, well, it's not problematic. It works really, really, really well. But actually, when you come from theories of everything, you find that that's rarely the case, getting these two perfectly separated. So non-minimally couplings to gravity that they were mentioning in the question are these types of couplings that do not satisfy this separation. So imagine that you have some scalar field in the matter sector that suddenly also couples in some non-trivial way to the gravitational sector. If you allow that to happen, then you normally break the equivalence principle that we really like, but we don't actually have any fundamental explanation for the equivalence principle to be perfectly always satisfied. And that's kind of like the roots of the modified theories of gravity that I study, that they are very different to the very kind of famous theories that are called MOND, like modified Newtonian dynamics. The modified Newtonian dynamics, normally, they don't agree with general relativity at all. So they don't agree with that general relativity is right. And that's not the theories of gravity that I like to study, because the general relativity is fundamentally not only very beautiful, but it really kind of explains perfectly why gravity is around, and in a very natural way. If you can kind of make it work with matter and also the standard model, you have like a formalism that lets you study predictions out of it. So the only thing that we are doing in modified gravity, in the ones that I study that are normally called the scalar tensor theories, we can go into that later, is allowing for these non-minimal couplings to exist and see what happens. Because having the two sectors completely separated is an assumption that we don't know if the universe is taken.
So, Sergio, my question is that means, where are we finding exactly the limitations of GR? I mean to say, when we are putting in a modified theory, what are the questions that GR, or the field equation of Einstein, is unable to answer?
That's a good question, because okay, so we know that there are things that we cannot explain yet. That doesn't mean that it's general relativity's fault, or Einstein's gravity's fault. Why do I say this? Because actually, we don't really know whose fault it is. We have basically two how is it called, two contenders. One is general relativity can be wrong, and the other is the standard model can be wrong. So in a way, you can basically add new ingredients to to any of them, in order to satisfy this new place, like this, or amend these places in the universe that we cannot explain. The main two, I would say right now, the biggest two questions are dark energy and dark matter. So dark energy comes from the expansion of the universe. From Einstein's gravity, the standard one, like general relativity, we can predict how the universe is expanding. So how do we do this? Is we have Einstein's equations. We put in Einstein's equations, you have two sides. One, as I was saying before, because it's separated, you have general relativity, like gravity at one side of the equation and matter on the other side of the equation. You can look around and say, okay, this is the amount of matter that we have around, because we have experiments. We can see it from also the cosmic microwave background. We can estimate how much matter and radiation there was back then, and we put it in one side of the equation. And the other side of the equation is going to tell us how the space-time evolves, how gravity changes. And what they found 100 years ago, actually Einstein was the first one to find this, was that the universe was going to either expand or collapse. It was not static. And if you know this story, probably you do, he added some terms into the equation that weren't there originally, because he thought that the universe was completely stationary, was static. Actually, you may think that that's something quite crazy, but when he was developing this theory, they didn't know. For instance, they didn't know that there were more galaxies. They didn't know that the universe had galaxies and there was empty space. They thought that everything was kind of homogeneous. So of course, it made sense for him to do that. However, some years later, I think that it was 10 or so, there was the first Hubble experiment, Hubble observations that he made, and he found that the universe was actually expanding. That was crazy. He also discovered that there was more than one galaxy, so he discovered Andromeda galaxy. And I mean, those two things are worthy of Nobel Prizes by themselves. And so just imagine. And it was, people said, okay, so Einstein was wrong with this. Of course, these ingredients that he added into matter in order to make the universe static, they are not there. The universe should be expanding. And people was really happy with that, because when you put matter, the universe expands, and they looked around and the universe was expanding. However, the problem came almost 70 years, 80 years later, in 1998, when better observations of the galaxies around us and supernovae, like actually using supernovae and all of that, and Cepheids and these kind of standard candles, they are called, they wanted to get a better estimate of how fast the universe is moving while expanding. And when they made these observations, they saw that the universe is expanding faster than they thought. But not only faster, the problem was that the universe was expanding in an accelerated rate. So tomorrow is going to expand faster than today. And there is nothing in Einstein's equations with the matter that we see around that could explain that. Every matter that we see around us would basically predict that the universe expands every day slower, but actually the universe is doing the opposite. Now, there could be some kind of energy around explaining that. And because this energy, we don't see it, and the only way we have to see is through light. So if light interacts with this energy, we would be able to see the energy around us, but because it doesn't, it is completely dark, it's invisible. So because it's energy that is around and we cannot see it, we call it dark energy. And that explains the expansion of the universe, but we don't know what it is yet. That's the kind of like one of the biggest questions in cosmology right now. And the other is similar, but with galaxies. And galaxies, we see that basically we know from Newtonian's mechanics or Kepler's laws, we know how two objects should orbit each other. And if they have too much, like we know that there's going to be an elliptical orbit, and if it has a lot of velocity at some point, then we know if the orbit is going to be elliptical and stable, or it's actually going to be unstable and a hyperbola. So it's not going to be able to orbit one object around the other. We know that for 300 years, 400 years, I don't know. But actually, when we look at galaxies, we see the objects orbiting really, really fast, too fast. So basically, if you see all the matter that there is in galaxies, and you had to explain the rotation curves just by the matter inside the galaxies, they wouldn't be stable. All matter should basically shoot off, and the galaxies should dissipate, but they don't. So there must be some kind of matter around the galaxies that does not interact with light once again, so we cannot see it. That missing matter that we cannot explain and does not interact with light, we call it to be dark matter. So it's two regions in cosmology where we see things evolving in different ways that they should, and in order to explain why that is, we put like a placeholder there, and that placeholder is dark energy for the expansion of the universe and dark matter for the rotation of galaxies. So again, is this the fault of general relativity? Honestly, I don't. In my personal view, even I do modify gravity. I don't think that is the problem with general relativity. I have a different approach to modify theories of gravity, but again, we know that it's someone's fault. It could be that there is new species in the standard model, or new particles in the standard model that do not interact with the photons, so they don't emit radiation, and so we cannot observe it. Or it can be that modified gravity, that there is a modified theory of gravity. Now, for like, it's right now modified theories of gravity for the expansion of the universe are okay, like they can explain it quite well, but they cannot explain really well the rotation curves in galaxies. So the only thing that we are doing is kind of having these two contenders and saying, okay, let's try to test them. And right now it seems that is the fault of standard model. General relativity seems to be very, very well. But as I said before, we don't have any reason to believe why general relativity should be behaving so well. When you go to these theories of everything, they never predict something that close to general relativity. So what we are doing is kind of finding places to test for these differences or these deviations. And so far, we haven't found it.
Absolutely. Thank you very much. That gives a complete account of the, I won't say limitations, but yes, certain limitations of GR and how we are. I have got my questions, but before that, there are a lot of questions which has
Yeah.
already
By the
come
way,
up.
feel free to interrupt me at any point. I don't have. I talked a lot. Sorry for that, but
No,
feel
no,
free
that's
to.
fine. We were actually waiting for this kind of a detailed understanding. We'll take one question from one of my favorite student. Kankana is telling that if the basic concept of inertia or conservation of mass energy momentum does not hold true in the smallest scale, how revolutionary is that? What is the reason for it?
I don't. I don't. I don't know what she's or yeah, she right. Yeah. Yeah, thinking of. is it in terms of quantum mechanics that there are some concepts that are not satisfied? Is that where maybe you understand better the
I
question?
also, I am, yeah, I would request Ankana to put it in a more better way so that we can
It's fine. So
understand.
if it's in terms of quantum mechanics, then I believe that I mean I understand. Yeah, it's revolutionary. Probably because she's on inertia. Oh no, this is the same. Sorry. So yeah, that is revolutionary, and I really like that. I really like when I teach, like when people kind of think that physics is kind of crazy or non-intuitive and revolutionary, because that's how it is, and when and that's the best thing of physics. That's why we love it, and it happened 100 years ago when quantum mechanics was being discovered. That of course it went against all our intuitions in so many levels,
Right.
and people thought that it was wrong, and of course and crazy, and of course they thought that it was wrong and crazy. But I think that is the thing that I like the most about our universe, is that it's not intuitive at all, and every time we try to impose our intuition to our universe, it turns out that it's wrong because the universe is much cleverer than
Absolutely.
us.
Absolutely.
But I think that
Yeah.
sorry, go ahead.
No, no, please go ahead.
No, yeah, that the fact that you have inertia being not, or energy momentum being conserved, is not, well, inertia and energy momentum is the same thing. So yeah, having like the energy of the system conserved is not too problematic. Well, in quantum mechanics, energy is always conserved, and momentum, you have some error in the system. But again, it is normally the case that what quantum mechanics is telling you is that you are asking the wrong questions. That's the best way I have to understand quantum mechanics. We tend to think that there are questions that are perfectly valid, like saying, what is this particle? And our intuition, because we were, well, our intuition comes from the evolution process of many million of years of the Darwin theory. So of course our intuition was shaped to understand classical mechanics, not quantum mechanics. So the questions that we may be asking at low scales, where at very short scales, that we never see, and so we have never been able to shape an intuition around them, sometimes they are just the wrong question, and we cannot ask them. So where is this particle? Sorry, this is the wrong question. That's not how it works. Things are shaped in waves. It's like if you go to the sea and you ask, what is the drop of water? It's like, well, it's not like the drop of water. It's something more complicated. It's a system. It takes a shape in space-time, and then you can ask a better question. You can say, okay, what is the concept? Well, it's not perfectly like the best explanation. Like, it has some limits, but I'm talking in terms of the things are waves now, and that's what they are like. Nature is telling us that in the microscopic and, well, no, nanoscopic scales, things do not behave as tiny particles going around, like as as tiny balls around. It's more like things are waves, and you cannot ask the same questions to tiny balls as to waves. So you need to change your understanding and the questions you are asking. So position is not something that you can ask to a wave, because it
Right.
is extent, right? It covers the whole space. You can ask, what is the probability if I'm asking at some point for a peak, what is the probability of that peak in the wave function to appear? And that's what we call a measurement. So it's going to have a probability. It's crazy, yes, but actually energy is always conserved in these systems. That's actually a good question. So
Yeah.
yeah.
Yeah, we have got another question which is very relevant. But before that, I would like to ask you now, you being a theoretical cosmologist, now, as because most of the people, the 2022 people who are listening now and more will be watching later, they are students. So there are questions, for example, imagination in terms of the large scale expansion of the universe. For example, it's huge. I mean to say, how big it is. You cannot give regular objects, for example, anything, a big field or a meadow or something like that, which actually gives you an understanding of hugeness. That means how big it is. How do you do that when you are doing the mathematics? What would you suggest for the students to do the exercise of a huge imagination?
Okay, so you talk in terms of having like like developing the imagination, not the way we deal with it in physics. Yes.
Absolutely. Yeah.
So this is I love this question. It's a really good question. So actually, this is something that I've been doing since first year in undergrad. It goes little by little. Like, of course, you need to first grasp. I would say that the mathematics, honestly, the mathematics for describing how the universe evolves normally are not more complicated than something that you do in undergrad. So yeah, normally it's important to do mathematics to get all of that, but normally what it takes really, really long is understanding why you are using that equation, and basically being you the one guiding that equation instead the other way around. You need to be the one in control. In terms of imagination, this is an active curve that I've been doing, and maybe people don't do that much, but I really enjoy doing it. So in my case, when I was on it, like it goes like that. Like I'm waiting for the bus. I'm like in a situation that I don't want to be in. Like I'm bored, basically. Normally, I get distracted a lot, so it's not like I'm perfectly doing it all the time. But if, for example, I'm in the bus, I'm suddenly in a dinner that I don't want to be in, or all these situations that you have to be waiting and you don't know what to do, I always really, really love to kind of improve my mental laboratory, I call it. So kind of I normally, every time I think of a galaxy, I realize that I'm always think of the same galaxy, and I can imagine the galaxy suddenly rotating faster and kind of making simulations in my head. The first time you do that is very, very difficult, because I mean, you don't have an image to start with and all of that. Then you think of the expansion of the universe, and there are all the scales. But what I'm thinking when I see the expansion of the universe, for example, in my case, is like a liquid, because when you zoom out the universe, you zoom out and zoom out and zoom out, you stop seeing the individual galaxies, and what you see is like a fluid. And actually, what you use, the mathematics you use to describe this, is fluid mechanics. It's not the single galaxies being around. So in that sense, it's very important to basically, I really like reading books, for example, like I did it during my undergrad, like reading these outreach books that there are around, because I didn't understand them. I didn't really got the grasp of everything, but they started putting some kind of image in my head that I can see now, that I kind of go back to every time I'm imagining something. And this is an active work. Like, I wouldn't say that this comes just naturally. You have to put effort, and I would say that my favorite part of doing research, understanding. And in order to understand, in my case, I really like to have like an imagination, a simulation in my head on how it is evolving, in order to see if something is being weird or not, because it gives you this kind of intuition.
So here is a point that if you are on a dinner which you are not liking, or in a long journey in the bus, try to expand your mental laboratory, as Dr. Sergio has told. And I think this is a good exercise. So you are suggesting that imagine something too big, which is out of your mental intuition, and then try to put all the thinking into there and see what are the complications, and then slowly, one by one, get out of that and find something which is very concrete and feasible. I mean to say that kind of an exercise would do.
Yeah, exactly. And
Okay.
try to relate it to things that you already know first.
Yeah,
Like, as I was saying
right.
before, the expansion of the universe is just a fluid. It's
Fluid,
some kind
right.
of fluid that
So
is.
this, yeah, yeah. So again, just to tell all of you who are listening, this is an excellent advice. I missed on this part to earlier, guest speakers. So imagine the universe to be a fluid. When you are on a long drive, or when you are relaxed, to try to do this kind of exercise. I would like to show you another book, Sergio, that you're talking of. The mistakes which people make. Now I'm reading the second time this book called Brilliant Blunders, and it starts with 5 mistakes, starting with Charles Darwin, Lord Kelvin, Linus Pauling, Albert Einstein, and I think I forgot the fifth name. Should be I think the DNA structure. So there are 5 scientists who actually made big blunders, and I'm just completed Charles Darwin, and I'm moving with Lord Kelvin, who made certain mistakes with calculating the Earth. I would strongly suggest you also. It is a little bit heavy read. I mean to say, there is no mathematical equations that even makes things difficult. So here you can see this. These are actually, the content. And this is a wonderful book which actually tells that Albert Einstein made the basic problem, that was cosmological constant. And this is Marie Olivio is one of my favorite authors. This is a very good book. I just finished one called Edwin Schrödinger and the Quantum Revolution. That also was a great read. Okay. I will come back to the questions quickly. Now, Joker is asking, I don't know what is his name, but anyway, yeah. So graviton, a particle that carries force through space, very weak detected. Can we have equations for those graviton particles like we have Maxwell's equation and Einstein's equal to hf? Actually, that was also my question, Sergio, that is a modified theory of gravity also trying to find out graviton or try to unite quantum physics and general relativity? Over to you.
Well, it depends, again, which theory of gravity, like modified theory of gravity you are working with. The ones that I work with, again, of course, I'm going to be biased in this, they have gravitons. Now, the notion of graviton, we don't know if it's true. We hope to be true, because the graviton is a quantized kind of, like a quanta of a perturbation of the field. So you have normally the Higgs field or the electron field in quantum field theory. This is the way we understand interactions. So in the standard model, we know now, because it's like in quantum field theory, that we have fields, and this is one, I kind of go to one step back always to put like the base on the answer. One of my favorite questions in all kind of physics, that is, what is the probability of two electrons having the same charge and mass? And all electrons we have seen around, they always have the same charge and mass. It's like, how is that they all have exactly? They don't, you go to the 10th decimal place and they don't take a tiny different value. How is that possible, that you can have all the particles in the world, but they always tend to always have in the end the same exact properties? And this is what quantum field theory answers. Quantum field theory, what it says is that instead of having particles, you have fields. And there is only one electronic field. And the perturbations of this field, like quantizations of this field, are the different particles. So I always kind of like to go to like an example, in classical example, as I was saying before, this really helps me. Like if you, for example, it starts raining, okay? And you see all the rain, and you don't know that there is a cloud above you. You just know that it's raining. And you start taking drops of water from this rain and compare one with each other. And you see that the chemical properties of each drop of water is the same always. And you say, that's really weird. How is that all the drops that comes are exactly equivalent? And then you understand that it's not like the drops of water are distinct. They come from the same cloud. And because the cloud itself has some properties, all the tiny drops and quantizations of the cloud, in a way, that gets formed will have the same properties too. So this is what is happening in quantum field theory. You have like a cloud in the universe, and the drops of water are going to be particles in this sense. This is the way we understand all particle physics and the standard model. If you want to do the same thing with gravity, so we have a field in gravity. This field is the metric, is the space-time itself, what says how the space-time is being curved, or what is the shape that it has. You could say the same. What if I make kind of like a wave in this metric, in this field, in the space-time? Is there a wave, like a minimum wave that you can create? That minimum packet would be a graviton, but we don't know if that is around still. We have mathematical formalisms to say that it could be there, like in order to work with it. And actually, that is, I would say, my thesis was on actually that, trying to find how gravitons interact in modified theories of gravity. And I built a package, like a numerical code and all of that in order to predict it. And yes, we have equations similar to Maxwell equations, but for gravity. And they are, I guess that they are called Pierce-Pauli equations. Well, it's not exactly, but it comes like what comes out of the Pierce-Pauli action, that I don't know if you know what that is, the students, but it's just some kind of fancy formula where you can get equations of motion from. So from that fancy formula, when you get equations of motion, you get the equivalent to Maxwell equations, but for gravity. We don't know if they are right, because we don't know if gravity can be quantized.
Right.
That's the final answer. The theory of everything would be a theory that lets gravity to be quantized and not lead to very big problems in the whole
Absolutely. And in some sense, you see that this was an absolutely wonderful example which you just gave, and I will like to thank you for that. If the water drops are falling, how come it is all the same? So we have in QFT different types of field, electron field, then we have got even proton and neutron. These are all excitation, perturbation of the field.
No,
This
not
brings
the
to
proton and neutron, because they are not fundamental particles. So proton and neutron and
fundamental particles, right? Okay,
so it's
yeah.
only elementary particles, yeah.
Elementary particles. So this actually, I will just like to ask you, Sergio, that means the physics that happens when general relativity breaks down at singularity or near the event horizon, when we see the particles which are popping up. So is modified theories of gravity also trying to address those issues, especially at singularity, how things will happen?
I wouldn't say so. No, I don't think so, because we have no understanding of GR there, like fully understanding of standard general relativity in those regions yet. So it's very difficult to actually extend them to modified theories. Normally, it's more difficult to go to modified theories of gravity. Now, you could argue that in a way we do have like this. There is like a modified theory of gravity, and it's not because we have measured it, but you have, as you were pointing out, this problem with the Hawking evaporation of black holes and the entropy not being like disappearing entropy. So the best explanation, well, the best tools that we have in order to understand that right now come from string theory, and some very, very complicated like idea that is called ADS CFT. They are letters, you don't need to understand them, because I don't, honestly. I just don't understand what is going on there. That's the mathematicians doing their own thing. I have done some kind of small courses on that. It's very beautiful what is going on, but I don't do research on that because I'm not expert at all on those topics. But okay, so what I'm saying is that where I'm going with this is that normally these ideas rely on the existence of kind of like having a string theory. Well, I'm not sure if they do right now, but they came from a string theory. That's kind of one of the examples of why a string theory is so valuable, because it gets us to new ideas that we wouldn't have arrived otherwise. So if a string theory is around, and it's true, if a string theory were true, then you would have a modified theory of gravity at low energies.
Right,
That's kind of
absolutely.
how I relate it. But I wouldn't say that modified theory of gravity actively is trying to solve those issues. It's kind of,
Right.
yeah, indirectly, they are kind of direct.
Yeah, I also think that, say, for example, when I'm making a series of more easy videos on what is called the Dirac equation. Now we see that the Dirac equation fundamentally could associate special theory of relativity and quantum mechanics into a kind of a unison, where one part is the special relativity, another is the quantum mechanics, which was not done by Edwin Schrödinger. Classically, he explained it. Now, what I also feel, maybe I would like your views, that the reason that special relativity united at the quantum level using the Dirac equation was that we were actually talking of what? The speed of light. It is basically made of photons. So ultimately, even if we don't consider the space-time, which was a flat Minkowski space for special relativity, if we take considering the speed of light, which are photons, ultimately it is uniting with what? At the quantum level, it is uniting with quantum physics, with Dirac equation, with the spinors, etc., wave function, etc. Now the problem that we are all facing, I mean to say, I'm also into general relativity, is that this gravity is something which defies to unite on a very quantum scale. Even if you take special relativity, the speed of light, even if we integrate light, it is photons, so it is quantum to quantum. So there are possibilities that how beautifully Dirac equation united special relativity with whatever complexities it had. That is not an issue. But the problem we are facing is that gravity works on a much larger scale, where we have not found anything which are related at a quantum level. Now, if you say that, as you were telling, that modified theories of gravity do include graviton, and if we can find that graviton are something which are interacting at a field level, then perhaps we can unite gravity at the quantum level. What are your views in that case?
Yeah, no, I'm not saying that modified gravity includes the graviton. There is still like, we don't know if GR, because modified gravity, the ones that I study, are just an extension of GR. GR is general relativity, by the way. I don't know if I said it before, but we don't know if GR will have gravitons. It will be quantized or not. We really don't know. So I wouldn't say that modified gravity includes graviton. So if you find a graviton actually around, it's going to be difficult. There are experiments in order to find gravitons, but they are very, as you were saying, very, very weakly interacting. So these experiments require like very, a precision that we don't have yet. If you found a graviton, that wouldn't mean that there is modified gravity. That would be a problem, I would say, because then it means that all the implications that we are finding from general relativity and quantum field theory, there will be something that is not matching. Because as you were saying before, the problem, like quantum field theory, what it did was taking classical particles and a Schrodinger equation, or quantum mechanics and special relativity, and joining them together. As you know, special relativity is the simplest case for special relativity is the simplest case for general relativity. So when you don't have any matter around, like spacetime is not curved, you would have special relativity. So in a way, it works in the first step, but when we try to put matter around and curve the spacetime, things start getting more and more complicated. And
Absolutely.
And the problem that you are saying is called, I think that is related, to the cosmic censorship theorem, that is, or conjecture. Conjecture. That is that the universe is very, very, it's not putting things easy on us. Because if we wanted to find the theory of quantum gravity, the best thing that we need is to find interactions of the graviton with matter, as you were saying. That's the first place you would look at.
Absolutely.
But of course, in our colliders and in everything we have around, it's very, very difficult to do that because gravity interacts really, really, really weakly with fundamental particles that they don't have any energy. They have some mass, but again, the other way around. They don't have any mass, they have some energy. But again, it's almost like the interactions are very, very suppressed. So you need a lot of matter in order to find how gravity is going to interact with these particles, with quantum mechanics. But in the moment in which you have lots of matter in some point, and what happens? Suddenly you create a black hole.
Black hole, right.
So in the moment in which you would be able to test quantum gravity, like any point of space-time, you have enough matter to test quantum gravity, suddenly the universe protects itself and doesn't give you any information about it because it creates a black hole. So you cannot see what is going on inside.
Right. Absolutely.
The other place where that happens is the early universe. So in the early universe, we cannot see what is going on because it was completely opaque. There was no light traveling. So the universe, every time we want to get closer to an experiment in our observation to see quantum gravity, the universe has always a way, or gravity or whatever, always a way of hiding it from us. So it's putting things very difficult.
Yeah, absolutely. Quick questions coming up. We are almost near about an hour. Jason is asking, could Sergio please name a single experiment that has discovered any dark matter?
Well, we haven't discovered dark matter directly. That's kind of the whole thing. We have many reasons to believe that there is dark matter, and we know a lot about the properties of this dark matter that it should have. The main one is the rotation curves of galaxies. And then there is where all these theories like Mond come along and they say, okay, I have this explanation that if you change Newtonian dynamics, we can explain the rotation curves of galaxies. But they are not enough anymore because we also know a lot about structure formation. We know that with the universe, in the early universe, you had basically everything was kind of homogeneous. You have some types of perturbations in matter. And these perturbations led to the seed of galaxies. And these are the galaxies that we see right now. So we know that also, if you don't have dark matter around, you wouldn't be able to explain the amount of galaxies or the correlation between galaxies and how separated they are. You wouldn't be able to explain it with a standard gravity and a standard model. You need also the dark matter to be around. So we don't have like direct experiments that have found a particle and we say, hey, this is dark matter, we have found it. If we had done that, then there wouldn't be any argument. We know that there is a particle that is called, say some name. It could be, there are some contenders again, like the axion, the WIMPs, and so other particles. But again, it could be PBHs also, primordial black holes that they were formed really early in the universe and they are around and we don't see them. there are many different contenders, but we don't know which one it is. We just know that it is around because we have many different evidence for that, and from that evidence we also know what types of properties these contenders for dark matter should satisfy.
Right. Thank you very much. Next question asks, what is the use of embedding class on class 2? I don't know. Is it class 1 and class 2?
I
I'm also,
don't really
yeah, I'm
understand
also
this.
not very sure.
This sounds very mathematical for me.
Yeah, absolutely.
Yeah,
Uh,
so-
uh, Next question is, sir, can you please tell about FLR? I think he was talking of the FR gravity and its impact on cosmology. It's one of the modified field theory.
Yeah, it's one of the theories. And f of r, LM, I don't know what it refers to, but it's fine. Like I will talk about f of r. And these f of r theories of gravity, basically, okay, we have to go into equations. I don't really like doing that in when I do outreach, but it's important to do this. If you remember earlier when I said that gravity was a split, well, or a standard gravity or the standard model, and cosmology splits gravitational sector from matter sector, so they are split. And modified gravity, what it tries to do is to join them. That's what I said earlier. Well, in a way, I was lying, not a lot, but those are a subset of these modified theories of gravity, the ones that I study. A different thing that you can do is taking this gravitational sector and change it a little bit. Right now, the way the gravitational sector is described is by saying that the way a curvature is going to propagate, that's like propagate, is going to be given by whatever minimizes the local curvature. That's the whole thing. And the way you measure the local curvature comes from differential geometry. And if you know anything about differential geometry, it is basically the Ricci scalar. That is when you trace twice the Riemann tensor. That's not important again. Now, say that's something that I asked from the equations I was saying before. This comes from Einstein, not really, but kind of assuming that was the theory of gravity. But why it is R? Why is only the curvature? Why is not the curvature squared? Or the Riemann tensor traced with another Riemann tensor? Or different objects of pure gravity, but coupled in a different way? Well, we know that because the higher order you have, the higher number of different curvature terms you have, they are going to be more and more suppressed. That's normally how it works. Well, we know that it works like that. So if they were there, you could have just like the leading order term in the whole gravitational sector. The leading order could be just the curvature term that we are measuring, the one that Einstein put, and then have subleading terms that are these terms like curvature squared and things like that. So you are modifying gravity in a different direction. Instead of allowing for couplings between matter and gravity, non-minimal couplings, what you are going to be doing is adding new kind of functions of gravity in the gravitational sector. So it's still split, but it's different. Those are the F of R theories that they were mentioning in the question. And actually, something really cool about these theories is that you can show from the equations of, like, you derive the equations of motion and like substitute them back, they are actually equivalent to the ones that I was talking about earlier, these scalar tensor theories, the ones that you could describe, basically. I'll say it again. The two different theories of gravity that I was mentioning, ones where you have couplings between the two sectors and ones where you add new species into the gravitational sector, actually you can show that they are equivalent. You can find equivalent theories to describe one in terms of the other and vice versa. So yeah, they are like very interesting contender, but you can describe them with scalar fields, which is really nice.
I'm taking up a little bit more time, Dr. Sergio. A few more questions are coming up. Just
I don't have
before
any time constraints, so it can.
Okay, fine. That's great. One question is that means in modified field theory, or whatever the research or the mathematics I'm interested that you do, that it involves the same metric tensor, Ricci scalar, Riemann tensor, differential geometry. It includes those things only, but it takes up to, I mean to say, another level. Is that so? The
Yeah,
mathematics.
exactly. So that's what I meant earlier when I say that I respect a lot general relativity, and I believe that general relativity is right. Because one thing is general relativity, that is the formalism, and another is the action, the sector, whatever you put, the ingredients you put in order to say what is the strength of gravity. Those are two different things. General relativity, I mean, it's honestly like very close to whatever the truth it is, because it works so well. And also it's kind of like, I mean, it's very beautiful the way it works. It explains so many things that we wouldn't be able to explain otherwise. So yeah, it depends on what direction you take. You would just have the same type of terms there, like the Ricci scalar, the Ricci tensor, or whatever, and just change it a little bit into different directions. Personally, the ones that I work on, scalar tensor theories, they are called, what you do is take a scalar field and couple it to the Ricci scalar. That's the ones that I study the most. So basically, you have like now this type of coupling. So if the scalar field is constant, it will look very, very similar to standard general relativity, because then it's going to have, you're going to recover just some constant times the Ricci scalar. But these f of r theories that they were mentioning in the question would go in a different direction. They would have also different terms for r squared or r mu nu, like different types of couplings of gravity with itself. But again, you can also express this as a new scalar field. So they are a type of similar.
Thank you. The question that Kankana asked, now she is telling that recent research from Durham University made news claim to have built a new theory of gravity in which the law of conservation of energy momentum tensor is not required. My question was on that, sir. The paper was named non-conserved modified gravity.
I'm not sure about that paper. Can you put the question again, back up again, so I can read it? Okay, there you go. So it's a theory of gravity in which the law of conservation of energy momentum tensor is not required. So, I mean, it's not, I'm surprised, because actually it's normally the case that modified theory of gravity will not conserve the energy momentum tensor. And not only that, but I mean, it depends on what you call conservation. Gravity does not conserve it either. It conserves it not with the standard time derivative. You will need the covariant derivative that comes from differential geometry. So the energy in the universe, whatever you measure energy in the early universe, is not the same energy today, for example, of some system. That's something that in general relativity we are already comfortable with. And then something else that you can do is not conserve, like covariantly, with this new derivative, the energy momentum tensor. That is normally the case for all modified theories of gravity. But I wouldn't say that is a big problem, because as I was saying earlier, you never know where the conservation is going on. Imagine that you have the standard model, or the lack of conservation is coming from. Imagine that you have the standard model and standard gravity. But in the standard model, you add some new species, like some new photon that we are not able to see. Then you will have the standard model, and through the emission of these photons that we cannot see, like a new kind of particles or photons, then the system would be starting losing energy. So from our eyes, it would seem that energy momentum conservation is not taking place, because you start with some energy and the experiment ends with less energy. But what you don't know is that there has been particles being emitted that you cannot measure. So again, there is not the biggest of the problems, because we don't, like, physics doesn't rely on the energy momentum tensor to be conserved. We can deal with that. It is inconvenient, but we can deal with that.
Thank you. Joker is asking, what are you currently working on, Professor Sergio?
Well, I'm not professor, but thanks for for considering me one. I'm actually working right now on these theories of gravity that include a new coupling to the Ricci scalar, like a new scalar field coupling to the Ricci scalar. So basically, it's like having, in a way, is very cool, because remember what I said earlier with the temperature. The scalar fields shape the temperature of the room, and then I said that the Higgs boson, what it does is it does the same thing in the universe. It sets a kind of temperature or a kind of value, and depending on this value, the quarks and elemental particles, electron and so on, they will take some mass or another mass. The ones that the theories that I study, do something very similar to this, but instead of changing the mass of elementary particles, what they do is change the strength of gravity. So gravity, depending on the evolution of this field, gravity could be more strong earlier in the past, like in the early universe, than today, because now you have this scalar field mediating that value. Those are the ones that I study. And where I study these theories particularly is in the particle sector. So if you go like into the perfect definition of what I am in physics, because everything like physics keeps you need to be more and more technical with time, is what is called a particle cosmologist. So basically what I'm doing is testing the impact that modified theories of gravity would have on the standard model and other way around. So I have also worked on the expansion of the universe, on dark matter. I've also worked in this on galaxies and see the impact, what impact they would
Absolutely.
have.
I think I can give all the links of your beautiful work
Okay, yeah, that's
in the description box, and the subscribers can go
yeah.
and
Sorry
check it.
for
Yeah,
interrupting. Yeah.
that would be great. Okay, there's a question from Sandeep asking that what are the difference among classical gravity, semi-classical gravity, quantum gravity, and modified gravity?
Okay, so that's a really good question. Classical gravity is the one that we are working right now with. General relativity, there is no graviton. I will jump to the other side. Quantum gravity is there is a graviton, and so gravity in the shortest scales behaves quantum-like. We don't know if that is the case yet. Semi-classical gravity is when we try to describe how quantum mechanics would affect gravity. But because we don't have a theory of quantum gravity, what we do is kind of make some approximation of taking what we already have and kind of go halfway there in order to make some calculation and some approximation of what it would happen. That is what we call semi-classical gravity. And then modified gravity goes in a completely different direction. That is like one axis. The classical, semi-classical quantum gravity is one axis. And modified gravity, what it does is just change how gravity behaves. The gravitational sector that I was calling earlier. So it goes like in two different axes. You can modify gravity and you can have quantum gravity.
Absolutely lovely, wonderful. I think it actually, I think we should call you as a professor because you're talking like a professor and you're teaching us. So there's no problem in that. A very generic question, but it's a very pertinent question. I think I have made a lot of videos and I'm still working on that. Mainak is asking, what is the way to learn general theory for beginners?
General theory is general relativity.
Yeah, general relativity, absolutely.
Okay, so for beginners, it depends on what it means beginners. Like the best way is going to university and taking the always the cosmology and mathematical route or theoretical route in the university. And at some point, yeah, normally it's in the fourth year of university, or in my case, I did it in the UK, so it was in masters. You do general relativity. But in my case, probably I was like you, that is that I wanted to know about general relativity before they gave it to me. And normally that requires extra work. It requires, well, not only extra work, is that you don't have the tools. So you're not going to understand by basically most of it. And it's fine. Like normally in my case, I read the books and I really enjoyed it, although I didn't understand really basically anything. Now, the
Sorry
books
to
that
interfere in between, just in between. Can you suggest the name of the book which you read,
yeah,
if
yeah,
you
I was
remember?
going to do that now. So the one that I read, I was in 1 year earlier. So when I read this book, so I really like it. It's called Space-Time and Geometry by Sean Carroll. Sean Carroll is just amazing. I don't know if
I
I
was
can.
just about to tell that. In fact, I suggested in one of my videos that the
Mhm.
first book would be Sean Carroll's Space-Time Geometry. Please go
Actually,
ahead.
I studied that book 1 year earlier, and then when I was in Cambridge for masters, he came to give a talk and he signed the book for me. So it was very special. I really liked like that. And
That's
the
amazing. You should
yeah,
have that with you. I mean to
yeah, I
say
have it
that's
with me. I can show it to you. I think that I have it over there. Let me give
yeah.
you one
I
second.
just
I'll show it to
yeah,
you.
yeah, sure, sure.
So this is the book, Special Space-Time and Geometry by Sean Carroll. This book is really mathematical. So if you're a physicist and don't know basically anything of differential geometry, but you are a physicist, that's important. Like you have to already have notions of classical mechanics, Lagrangian mechanics, all of that. Then this book is good. And then so I bought it, and then when I saw him, he signed it there to Sergio and the Einstein's equation over there, Sean Carroll. Which is amazing. I mean, it's one of the things that I most, most valuable that I have. Then, Then the thing that other books, if you're not a physicist yet and you want to learn a little bit about it, I would recommend Sean Carroll, the same author, just released two books recently. Well, one book like a few years ago, and another book recently, that is called The Biggest Questions in the Universe, something like that, or The Biggest Ideas in the Universe. I don't know the exact name, but it's Sean Carroll, the same person. And these books are meant for people like they explain from basically no understanding to all the way to, I think that the first one goes to Einstein's equation and the second one explains quantum mechanics. And I honestly say that there is probably few people in the world that could explain or understands quantum mechanics better than Sean Carroll and the implications of all of that. So I really recommend that. And again, they are very heavy. So you are going to have to read through the books and they are going to be difficult, but you are in the best hands, I would say. And then there is these other similar books that are by Leonard Susskind. Yeah, Leonard Susskind. And they are called the Theoretical Minimum, I think they are called. And they are a series of 4 books. I think that the first one is Classical Mechanics, second one Quantum Mechanics, third one General Relativity, and then Quantum Field Theory, something like that. But these Theoretical Minimum books by Leonard Susskind are also really good for this. They are way more complicated than just outreach books, but you don't need to be an expert in physics in order to understand them.
Absolutely, absolutely. Mainak is telling, wow, I also have the signature of the author in one of my physics concept book, H.C. Verma. You might not be knowing, H.C. Verma is actually a very big physicist and a writer from India. And he actually, so that is out. And I am also too excited to see that book, right? So I also recommend it in the same way. So I think we are going in the right line that, first of all, if you really don't know differential geometry, then Sean Carroll's book is the best. And a person like you who has got a signature actually helps you a lot in automatically learning without reading that book. So that's wonderful, right? One question which is pertinent to that, I generally suggest to my students that before going to into general relativity, if you're talking of the mathematics, for example, tensor calculus, etc., a good learning or understanding of differential geometry would enhance for a better understanding of general relativity. Do you think it the same way?
Yeah. I mean, general relativity is basically Einstein. What he did 100 years ago was learning, or in a way, rediscovering, or well, no, not rediscovering. He learned, and it took him like 10 years to learn differential geometry in order to apply what it was discovered by mathematicians like for decades earlier, and try to apply it to physics. So everything is differential geometry. There is no, then you can have the physics part and the intuition, what we were saying before, this way of imagining what is going on and having some relation with what happening in the universe. But general relativity is 100% all differential geometry.
Absolutely. Thank you very much for confirming that. And as I again will tell to the subscribers, see, Dr. Sergio is also telling, I am also telling. So please do concentrate more on differential geometry. Yeah. Okay, quick questions. We have a lot, so let us go one by one. Thick Physics is asking, sir, why does the variation of the action with respect to rescaling the metric tensor must vanish?
Okay, let me think. Variation of the action with respect to rescaling the metric but vanish. Okay, so I think that this question is kind of more specific than it should. Probably we have seen that the basically the variation of the action with respect to anything always vanishes. Why? Because this is kind of like the biggest assumption in physics that there is. This biggest assumption that we have in physics basically is that we have some kind of quantity or some function that is called the action. And when you minimize this action with respect to any of the objects in this or degrees of freedom inside the action, you are going to find the equations of motion for a system. This is called the Hamiltonian principle or the least action principle. Why is that the case? This is a question that, got me crazy for years during undergrad. I didn't understand why. And I wouldn't say that I have a really big understanding of why. There is a point that we have to make a kind of like this assumption. It seems to work really, really well. That's the best thing that I can tell you. And the other thing is that if you study quantum field theory, and you will get, I don't know if you're doing that already, but if you get to study quantum field theory, I really recommend that. In the end, the best way we have to understand quantum field theory is it was I think that discovered by three people at the same time, but we know this story from Richard Feynman, is the sum of histories. I don't know if you know about it, but basically, you can explain how quantum mechanics behaves by basically say that you have an electron starting here, and you know that it's going to end up here, the electron. You sum all the stories, all the different histories of how the electron goes from one place to the other, and goes to the moon, goes there to India with you, and then comes back here to the UK. When you sum all the different types of stories that you have, all the different ways an electron can go from point A to point B, then you can also explain why quantum mechanics behaves as it does. But the most important thing that you find is that, say that you explain why everything works in the quantum physics like that with the sum of stories. But when you take the sum of stories and put more and more energy into the system, so instead of being a very small electron that doesn't have any mass or energy, you put more energy. So for example, the electron gets way more mass and goes away from the quantum scale, what you seem to recover is the principle of the least action. You recover that the action always has to be minimized in a system, and that will give you the equations of motion. So it's something very fundamental. Honestly, I don't expect you to say, okay, that's fine, I believe you. But hopefully at some point, I encourage you, if you like these kind of questions, to go to general relativity, quantum field theory, keep studying, and at some point, hopefully you will find a satisfactory answer for that, or even you will come up with a better one and revolutionize
Thank
the way
you.
we
Yeah,
understand physics.
wonderful explanation. Nova is asking, what is the best book for GTR, which you have already answered, and cosmology? Can you suggest any book on cosmology?
On cosmology, I would suggest right now one that is very recent and is amazing, is by Daniel Baumann. It's called Cosmology. Daniel Baumann. And it's the best book there is right now on introductory level to cosmology. Because you could go to maybe Weinberg and these very famous books, but I would say that they are a little, not outdated. Like they are they are an amazing guide, and I would recommend you reading them at some point. But
Right.
for starting, I think that this Daniel Baumann, I don't know if should I write it in the chat or?
No, I got it. I'm just putting
Okay,
the
perfect.
Amazon link over here, which will help people to get through it. So Daniel Baumann, Cosmology.
That one.
I think
And
this, yeah.
also, very important, I would say, I think that Daniel Baumann actually also has free notes that are very similar to the book, if you cannot buy it. So it's fine. You can go to the notes, just look for his website. But also, there is a lecturer, a professor in Cambridge, that he lectured me actually General Relativity. And his name is David Tong. David Tong.
David Tong. Okay.
He is the best, basically, lecturer, I would say, in the world. Also,
Yeah, absolutely. David Tong, Professor David Tong, Theoretical Physics, DAMTP. Right.
He has notes on quantum field theory, on general relativity, on symmetries in action, in string theory, in cosmology, and everything. And all his notes are just priceless. They are the best notes you can find on all these topics at an introductory level. So I would put also his notes on general relativity alongside Sean Carroll's book. And I would recommend you, they are completely free. Also supersymmetry, you have all completely free. If you want to learn any topic, go to his notes. And also he will give at the beginning of the notes a list of books that helped him writing the notes. So probably you can even expand your knowledge going to those books.
A little bit frustrating, but yet a motivating question coming up. Professor Sergio, I'm from India. I don't have a formal education, neither in physics or math. I still aim to be a physicist, and sometimes my heart says it is not meant for me, and I feel like giving up.
Well, I mean, it's difficult because it's true that physics. I mean, it's a difficult thing because in the end, physics should be for everyone, and it's for everyone to enjoy and to learn more and more and more. But it's very difficult to contribute in physics and to go to the last point and start doing research without formal education. And the reason why that happens is because, physics is very hard. You need to put a lot of time to it, and normally it's very difficult to do that on your own time. Now, I think that still, that doesn't mean that you cannot enjoy physics or mathematics. Probably you will enjoy it as much as I do, honestly, because then when you get to more and more into physics, well, the life is very different from a research experience as to a student experience. So the student part, I'm sure that you can enjoy it and follow the latest advancements. And I will tell you that just keep learning. Go to these books. There is material online everywhere. This YouTube channel is the best example for that. And probably you can find, I don't know if they are free, but I know that, for example, big universities like MIT, Oxford, and these
MIT,
kind
right?
of universities put their courses online. So you are not going to go as fast or as farther as someone that is a researcher or a professor in physics, but I'm sure that you will be able to enjoy it. That is the important thing. Just enjoy what the universe looks like
Absolutely.
and studying it.
Last question. Actually, Darwin has asked it. Anyway, I mean to say this can be something. I think what he is asking in this question is that what is your view about the fifth dimension?
Well, so the fifth dimension, I don't have like a specific view. I know that well, string theory is very famous for adding new dimensions. I don't know if you know that, but it requires 10 dimensions, I believe, or 9 dimensions, existing around. If there are more dimensions around, we surely haven't seen them. That's the best thing that I can tell you. And you have two ways of doing this. Basically, the geometry of a space-time can take different shapes. For example, I will give you an example. It could be flat. It seems to be flat, but we don't know why. It could be flat. And flat means that, for example, let's think about the Earth, 2 dimensions. Let's go 1 dimension less. This really helps, going back to my previous question. Simplify the problems in order to create a better and kind of image in your mind. So in 2 dimensions, say that you are in a globe. I don't have a globe with me, but it would be inconvenient. And you start working in 2 parallel directions. So you have a friend next to you, and you start working in a parallel direction, in the same direction. If you're in a flat universe or in a flat space, in a flat Earth, then both of you will keep walking and walking and walking and will never cross each other. However, in a curved sphere or in a curved universe, what you would have is that suddenly you start pointing in the same direction, but because you start going to the North Pole, suddenly you're going to meet each other. So curvature of the geometry of a space is important on how things move. Why am I saying this? Because if there is a 5th dimension around, or 6th or 7th or 8th or 9th or 10th, as string theory predicts, then they cannot be around, but they will have an impact on the universe. And the way you hide these new dimensions is by what is called compactifying them. So basically, you make them very small. You make them cyclical, like a tube. Like you have one that is not compactified and the other that is compactified, and you make it very, very, very small. So small that we can never see it. It's impossible to see it. But when you start making more and more like higher energy experiments that are more sensitive to the quantum mechanics and to the short scales in our universe, you should be able to see differences. And that's exactly why I say that modified gravity is similar to theory of everything, or to string theory. Because when you compactify, for example, these new things that I was saying earlier, with the differences that you would see in the universe, can be explained by these modified theories of gravity. So they are the best way of predicting what the string theory would do.
So that means compactifying what was predicted by Kaluza-Klein theory, that you get a tube.
That's the first way. But when you have, so that's the easiest way of doing it. Kaluza-Klein, 1 dimension more. We know that it's not there. But when you go to string theory, that you have 10 dimensions, the way you compactify these new dimensions, it's completely crazy. So there are like many, many different ways of doing this. I don't remember the name. It's also the Calabi-Yau. I think that is called
Calabi-Yau manifold.
Manifolds. So the way you can compactify them.
Okay, that means this compactification into smaller regions are done for observation, or for the for mathematics to become easy?
The mathematics do not become easy. I must say that. No, it's for observation purposes, because we haven't seen this. It could also be, actually, I think that Sean Carroll does also some research instead of compactifying them, extending them so much that we don't see them. They seem to not be around at all. So you can have these 2 extreme cases. But all of these 2 extreme cases, basically what they do is kind of create a hierarchy, some range of energies in which it looks like there are only three spatial dimensions. But if you go to a different, this other region of energies, very, very far away from us, then you will see the new dimensions that should be around because of the string theory and so on. So
Okay, great.
it comes from a phenomenological point of view.
Phenomenological point of view. Yeah, and there's one question. Just a second. He's telling that I was reading a paper on general relativity emerges from superstring theory, and I was stuck on this. So yeah, thank you for answering this question. And I don't think we. There's one question. This is classical field theory by Landau and Lifshitz good for understanding field theory?
I must say that I have not read Landau's books, but it's something that I really want to do. So I would say that it's amazing. Like these books are known to be one of the best books
One of the best,
for
right,
learning
right.
all topics. So they are going to be perfect in all different sides. The only thing that I would say is that the learning was different when the book was when the book was published than today. So normally there are books today that gives you more a gentle introduction to the topic and helps you get in. For example, maybe you start with the Landau book and it's too difficult at first. Then I would recommend looking for different material. Probably David
Right.
Tong's he will have
That
notes on
sounds-
that probably,
yeah, absolutely.
and then you can go to. But that happens also with Weinberg. Weinberg's
Steven
QFT
Weinberg,
books
yeah.
are the best, but they are not a good first read. It's better to start with something else and then go to Weinberg after that.
Do you prefer that a person should spend some years building up a very concrete base and then go into general relativity, or we proceed and then we get stuck up, we learn a little bit, again we come back, we proceed, we stuck up, and then we get back? These two ways, I mean to say, both works, but what would be your suggestion?
I would say that it goes with preferences. I took the second route. I went too fast, I would say. Like and that has very big problems, because then there is a point in which they are asking you to understand general relativity and you don't have the background, and you can do it. I mean, I did it, you can do it too. So
Yeah.
you just have to put the time, and it's going to be very frustrating because you will always feel that you are kind of getting behind everyone, and not being, you're not going to do well enough, and it's very difficult. It's a very stressing situation. While my peers, I remember in masters, for example, they had really strong foundations and they didn't suffer in that way as much as I did. So both work. I would, in my point of view, if you don't, unless you are like me, that you really need that now, and I wouldn't say that that is a positive thing, you are very impatient and all of that, then I would recommend you to build a strong foundation. And for that,
Right.
yes, normally university will help you. So don't overdo it. Like at some point, if you are in university, you're learning about this topic, like you're learning about each year to mathematics and physics, classical mechanics, quantum mechanics, all of that, and then you have to wait 4 or 5 years for GR, then wait for them, because I'm sure that once you get to GR, you will appreciate it. If you want to before that start getting some notions on how it works, then take the books, and on your free time do that, because without any pressure you will start getting some notions.
Absolutely.
So to see how it
Yeah.
works. So yeah.
Actually, my father, who is from IIT Kanpur, a metallurgical engineer, he suggested me that there can be two ways of learning. This first was taking up a traditional time, what you call university courses, building up the base and doing. And the second is also effective, because my father told that an engineer actually never build up a long base and then do into the problems. They go into that, they find something, and then go back. I need tensor calculus, I need differential geometry, etc. I will learn that part only, and then I come back and I go forward. So what will happen, as you rightly told, that the frustration won't grow, that for years and years of doing mathematics, nothing is happening. And in the meantime, when you get hold of the tits and bits a little bit, at the end of the year, you see you learn a lot.
Yeah,
And also you progress. I think
exactly.
that is a brilliant idea.
I
Thank
would
you.
say that if you want to do something different to engineering, I would say if you want to do like string theory, fundamental research, not phenomenology, not cosmology, like fundamental research, probably it's better to go slower,
Right.
because you really need the fundamentals to be solid in there.
Right.
That's yeah.
two quick questions. We are already taking a lot of time of yours.
No worries.
Locomotiva is asking, what did they expect to possibly see presence of extra dimension in LHC, not LHV? He corrected LHC and CERN experiments.
I would say none. No, there's no chance to see extra dimensions. That's probably what they mean, and it's not like that is not true. Normally there is like this news and not even propaganda, but like this news that they don't do probably their job well enough and gives you these headlines, and they are not true. Like you cannot find extra dimensions in LHC. What you can do is find new particles, and it could be
Right.
that the way these new particles interact can give you the hint of a string theory being around, and if a string theory is around, then there will be extra dimensions.
Extra
It's
dimensions.
very
Right.
indirect, but you will never in these colliders you will never open extra dimensions.
Right. Arches is asking, what was your path to GR? How did you come across it, and where did you read from? I think you have already answered that, telling that you came across Sean Carroll's book, etc.
Yeah.
So I mean to say that's it. Thank you very much, Dr. and Professor Sergio. It is really wonderful. I mean to say it was a very long podcast, more than as usual, but we got a lot of learning. I mean to say, see what I do. I will be very honest. After we end this, it is almost 9:30 in India, and then I will sit. I will have my dinner, and then I'm going to divide this entire long podcast into timestamps, that what you have spoken on what topics, and it gives me a lot of pleasure, although it is very tedious. There are so much discussions which has been done, and the good part is that we really learned a lot from you, and from cosmology, from GR, as well as modified theories of gravity, new things which are coming up. Thanks a lot. Any last message, Dr. Sergio, would like to give? Anything that you would like to share?
Well, thank you very much for inviting me over. It has been very fun. I know that the Indian community is very active on physics, and they're like you. Normally, I have some friends that they come from India and they are here and in the UK, and it's always wonderful to see how passionate you are about physics, and I love this, like what you're doing in this YouTube channel is very important. So thank you very much for inviting me over, and I hope you have
Right. We have got Professor Ashok Sen and others who are contributing significantly in string theories, and we are also, it is not based on India or UK. It is humanity as a whole. Last question is that in terms of modified theory of gravity, is there any real life applications other than, I'm to say, what we are doing to find out the answers?
Not yet. Hopefully someday, but we thought that there were no applications in quantum mechanics, and look
Absolutely.
at we are doing all this. So right now there is no direct applications.
Direct application. Priyo is asking, is Mathematica and Python really necessary for those who is doing PhD?
It depends on the project, so you will know. But in my case, I didn't know Mathematica when I started my PhD, and now I'm an expert on Mathematica, and I love it. So I had to learn. PhD is learning. So depending on what the project requires, is better. I would say that before learning Mathematica, like if you're doing like applying for PhDs, they will never expect you to know Mathematica, but it's really good to know Python. So I would say that Python is like a very good route for all physics.
Okay, fine. And here comes my friend, and I would like to thank him from Canada. And he says that this is the best physics learning channel. I'm so excited. So thank you very much, Dr. Sergio. And please pass on my due regards and thanks to Dr. Jessica. Yeah, because she was the one who actually contacted you. And you know what she wrote? That I've got a friend of mine who is an excellent science communicator. And today it has been proved. I mean to say, you explain things so easily, things so clearly. Okay, one question I don't remember is asking, is this because of conformal symmetry? I lost the reference to that. Is it because conformal symmetry? It is my opinion regarding what it is conformal symmetry. I think, is it 11 dimension is because of conformal symmetry? I really don't.
I don't really know the details of this. I'm sorry. I
Yeah,
mean, you had
absolutely.
yeah. Last week here was Joe Conlon, right? Probably he talked about that.
Yeah, absolutely. If
Well,
you ask me later, I can mail you and ask this question. That was
yeah.
that. So thank you, Dr. Sergio.
Yeah,
So
thank you very much.
how far you are from getting as a professorship? I mean to say, how many years down the
I
lane?
don't really know. This is very complicated in physics. Is you need luck and hard work. I'm trying to put the hard
Right.
work, but we'll see the luck. Normally, probably it would be for professor really long. For a permanent position, 4-5 years, something like that. We'll see.
Okay. So Durham University, I think they have got the best possible, infrastructure and facilities in order to do further researches.
Yeah, in the UK is one of the best ones. For
In the
particle
UK is one.
phenomenology is the best one. Yeah.
So you wake up in the morning and you sleep throughout the night thinking of those weird equations, and then get up in the morning, go to your school, university, and then start writing that. And then you start lecturing. I mean to say, you got a lot of lectures at Perimeter Institute and very reputed universities.
No,
So
no, I
you
didn't
go.
do lectures there. It was there were talks like about my research. So they were like
Okay,
like 20 minutes talks, 30 minutes talks. I tutor in Durham University. I have like some students and I tutor them every week.
okay,
I
you
don't give
tutor
like
them, right?
lectures, like big lectures. I don't give yet. You need to be a lecturer for that. It's like the next step. But
Right.
I look forward getting to that stage. I enjoy a lot talking about physics and explaining it, as you can tell.
Right.
So
So when you teach them, when you tutor them, it is on the modified theories or any part of physics,
no,
geometry.
no. So it depends on the module. So for
Okay.
example, normally it is like they are undergraduates. So normally it's
Okay.
first year physics or second year physics. And I really like to kind of what I did today, trying to get rid of all the technicalities and difficulties and show physics
Right.
what it is.
Okay. And my friend is telling physics should be an intuitive knowledge, and like Kung Fu, it may take a lifetime to master one area of expertise. I agree to that.
Yeah, that's why you can tell that from modified gravity and all of that, I can talk a lot. Then you ask about string theory, and it's like it's a completely different world for me. We know the
No,
same.
when you on your second and third email, I understood that what is your expertise. So I thought that let us divert our podcast towards this.
Yeah, that's
And Priyo is telling, I wish I could meet you, sir. The world is round. I think we can always.
yeah, at some point that would be nice.
Okay. Thank you very much. Thank you, Dr. Sergio. It's nice.
Thank you very much.
Goodbye. Goodbye. Good night. Thank you very much.
Bye.
Goodbye. Yeah. Bye.